Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore the most famous equation in the history of human thought. An equation so compact that it fits on a single line, so elegant that it has been printed on posters and painted on walls and worn on t-shirts by people who may not fully understand what it means, but who sense, correctly, that it represents something extraordinary. An equation that tells us something so deep about the nature of matter and energy and the relationship between them that even now, more than a century after it was written, physicists are still finding new ways to understand its implications. E equals mc². Energy equals mass times the speed of light squared. But what does it actually mean? Where does it come from? Why should mass and energy be related at all, let alone by a factor as strange and specific as the square of the speed of light? And what does it tell us about the universe we live in, about the stars that light the night sky, about the atoms that make up your body, about the fundamental nature of reality at its deepest level? Tonight we are going to answer all of those questions, slowly and gently, in the way that a story deserves to be told. We will begin not with equations, but with a train, and a stone dropped from a window, and a question about what it means to measure anything at all. We will travel through the thought experiments of Albert Einstein, through the strange consequences of a universe in which the speed of light is the same for every observer, through the dilation of time and the relativity of space, and we will arrive at the end at the most famous equation in physics, not as a formula handed down from authority, but as a necessary and inevitable truth that follows from the nature of the universe itself. So settle in. Let your body grow heavy and still. Let your breathing find its own slow rhythm, and allow the story of E equals mc² and the beautiful, patient mind that discovered it to carry you gently towards sleep. Albert Einstein was born on the 14th of March, 1879, in the city of Ulm in the kingdom of Württemberg, in what was then the German Empire. He was the first child of Hermann Einstein, a featherbed salesman who had a warm and easy personality, and Pauline Koch, a woman of considerable intelligence and musical talent who would pass both gifts to her son. The family was Jewish, secular in their practice, comfortable in their circumstances, and deeply embedded in the intellectual and commercial life of southern Germany. Einstein's childhood was not the childhood of an obviously destined genius. He was slow to speak, so slow that his parents consulted a doctor, worried that something might be wrong. When words finally came, they came in full sentences, quietly spoken, as if the young Einstein was already thinking carefully before committing himself to language. His younger sister Marja, who would be his closest companion throughout his childhood, remembered him as a thoughtful and solitary child who preferred building structures with blocks to the more boisterous activities that other children enjoyed. There was, however, one moment from Einstein's childhood that he himself returned to again and again in later life as the seed of everything that followed. When he was 4 or 5 years old, his father showed him a compass. The young Einstein was transfixed. Not by the compass itself, exactly, but by the needle, the way it always pointed in the same direction, the way some invisible force seemed to reach through empty space and pull it, insistently and without fail, toward the north. He understood, even at that age, that something was acting on the needle from a distance, through what appeared to be nothing at all. The mystery of it stayed with him. He said later that this experience shook him so deeply and left such a lasting impression that something hidden and deeply mysterious must lie behind things. Something hidden and deeply mysterious must lie behind things. It is as good a summary as any of the lifelong intellectual project that would eventually produce the special theory of relativity and the equation E equals mc². Let your breathing slow. The story of one of the greatest minds in human history is just beginning, and it is a story worth taking slowly, with the same patience and attention to detail that Einstein himself brought to the problems that occupied his life. Einstein grew up in Munich, where his father Hermann and his uncle Jakob had established an electrical engineering company that manufactured dynamos and arc lamps. The company was ambitious and technically sophisticated, and the young Einstein absorbed something from its atmosphere, a sense that the abstract principles of physics had direct and powerful consequences for the material world, that theory and practice were not separate domains, but aspects of a single endeavor. He attended the Luitpold Gymnasium in Munich, a school with a reputation for academic rigor and a teaching style that Einstein found increasingly stifling. He was not a poor student in the conventional sense. He excelled in mathematics and physics, as he would throughout his life, but he chafed against the rote memorization and the authoritarian structure of German education in the 1880s and 90s. He preferred to think things through for himself, to understand why something was true rather than simply accepting that it was, and the gymnasium was not an environment that rewarded this approach. When the family business failed and his parents moved to Italy in search of better prospects, Einstein remained in Munich to finish his schooling. He was miserable. Within a few months, he had left the gymnasium without completing his diploma, joining his family in Milan and announcing that he intended to apply directly to the Swiss Federal Polytechnic School in Zurich, the ETH, as it is known, which did not require the Abitur diploma that German universities demanded. He failed the entrance examination on his first attempt. He was 16 years old, 2 years younger than the other applicants, and while his mathematics and physics scores were exceptional, his French and botany were not. The principal of the ETH, recognizing the mathematical talent in the young German applicant, suggested he spend a year at a cantonal school in Aarau, Switzerland, to fill the gaps in his preparation, and Einstein did so. The year in Aarau was transformative. The school was run on principles very different from the Luitpold Gymnasium. It emphasized independent thinking, visual imagination, and the development of intuition alongside technical skill. Einstein flourished. He made friends, he developed a passion for sailing, he fell in love for the first time, and he began to think seriously about the problems in physics that would occupy him for the rest of his life. It was in Aarau, at the age of 16, that Einstein first posed the question that would eventually lead him to the special theory of relativity. He asked himself, what would it be like to ride alongside a beam of light at the speed of light? If you traveled at the speed of light next to a light wave, would you see a frozen, stationary wave of electromagnetic field? But Maxwell's equations, which described the behavior of light with mathematical precision, did not admit stationary electromagnetic waves. They only produced waves that moved. There was a contradiction somewhere, and the 16-year-old Einstein sensed it, though it would be another 9 years before he resolved it. He passed the entrance examination to the ETH on his second attempt and arrived in Zurich in the autumn of 1896. He was 17 years old. The ETH was a serious scientific institution connected to the great tradition of German and Swiss mathematical physics, and the 4 years Einstein spent there gave him the technical foundations he would need. But he was, even there, somewhat resistant to the formal curriculum. He attended the lectures he found stimulating and skipped the ones he did not, relying on the meticulous notes of his friend Marcel Grossmann, who would later collaborate with Einstein on the mathematical development of general relativity to fill in the gaps. What Einstein did during those years, more than anything else, was think. He thought about Maxwell's equations. He thought about the relationship between electricity and magnetism. He thought about the nature of light and the question of what it would mean to travel alongside it. He thought about the principle of relativity that had been articulated by Galileo nearly 3 centuries earlier, the principle that the laws of physics are the same in all frames of reference that are moving at constant velocity relative to one another. And he began to sense that there was a deep tension between this principle and the behavior of light as Maxwell's equations described it. The tension was this. The principle of relativity said that the laws of physics were the same in all inertial frames, all frames moving at constant velocity. Maxwell's equations were laws of physics. Therefore, Maxwell's equations should be the same in all inertial frames. But Maxwell's equations predicted that light traveled at a specific speed, approximately 300,000 kilometers per second. If this prediction was the same in all inertial frames, then the speed of light was the same in all inertial frames. But this seemed to contradict ordinary intuition about how speeds combined. Think about a train. If a train is moving at 100 kilometers per hour relative to the ground, and a person on the train throws a ball forward at 50 kilometers per hour relative to the train, then according to ordinary common sense, the ball is moving at 150 kilometers per hour relative to the ground. This is the Galilean addition of velocities, and it works perfectly for everything we encounter in daily life. But what if instead of a ball, we are talking about a beam of light? If a train is moving at some fraction of the speed of light, and a beam of light is sent forward from the front of the train, ordinary common sense suggests that the light should be moving at the speed of light plus the train's speed relative to the ground. But if Maxwell's equations were the same in all inertial frames, the light should be moving at the same speed relative to the ground as it is relative to the train. This seems impossible, and yet it was true. Drift a little deeper now. The story is approaching the moment when Einstein, sitting in a patent office in Bern, Switzerland, worked through the contradiction and found a resolution so radical and so beautiful that it changed our understanding of the universe forever. After graduating from the ETH in 1900, Einstein struggled to find an academic position. He applied for assistantships at several universities and was rejected, apparently because he had offended one of his professors by his attitude during his student years. He spent 2 years in a kind of professional limbo, taking temporary teaching jobs, before his friend Marcel Grossman's father helped him secure a position as a patent examiner at the Swiss Federal Patent Office in Bern in 1902. The job, which Einstein held for 7 years, was actually well suited to his temperament and his intellectual needs. He was required to evaluate technical patent applications, assessing the clarity and consistency of their descriptions, a task that exercised his ability to think precisely about physical mechanisms without requiring him to produce original research on demand. He became efficient at his official work, completing it in the mornings and spending the afternoons and evenings thinking about physics. In Bern, he formed what he called the Olympia Academy, an informal study group with 2 friends, Maurice Solovine and Conrad Habicht, with whom he met regularly to read and discuss philosophy and science. They read Mach and Hume and Poincaré and Spinoza, and their discussions sharpened Einstein's philosophical sensibility, his conviction that the fundamental principles of physics should be derived from clear and well-defined starting points, his suspicion of quantities that could not in principle be measured. It was this philosophical sensibility, more than any technical virtuosity, though he had that too, that enabled him to resolve the contradiction between the principle of relativity and the speed of light. The resolution required him to take 2 simple principles seriously, to follow their consequences wherever they led, and to be willing to abandon assumptions about space and time that every physicist before him had taken for granted. The 2 principles were these. First, the laws of physics are the same in all inertial frames of reference. Second, the speed of light in vacuum is the same in all inertial frames of reference, regardless of the motion of the source. From these 2 principles, Einstein derived the special theory of relativity in a paper published in June of 1905. Einstein was 26 years old. He was a patent examiner in Bern. He had no academic affiliation, no access to a laboratory, no professor looking over his shoulder. He worked with a pencil and paper, with the clarity of his own thinking, and with the courage to take ideas seriously even when they led somewhere unexpected. Let the image of that settle gently as you rest, a young man in an office, thinking carefully about light and motion and time, arriving at a truth that would transform the foundations of physics. To understand where E equals mc² comes from, we need to begin where Einstein began, with the question of what it means to measure things, and in particular what it means to measure time. Consider a very simple kind of clock. Imagine two perfectly flat mirrors, parallel to each other, separated by a fixed distance. Now imagine sending a pulse of light between the two mirrors, bouncing back and forth. Each time the light completes a round trip from one mirror to the other and back, we count that as one tick of the clock. Because the speed of light is fixed and the distance between the mirrors is fixed, the duration of each tick is also fixed. This is a light clock, and it is a perfectly valid timekeeping device. Now imagine two such clocks, identical in construction, synchronized so that they tick together. One clock is held stationary. The other is placed on a train moving at a constant velocity relative to the stationary one. The mirrors on the moving clock are oriented perpendicular to the direction of motion. They face up and down, while the train moves horizontally. From the perspective of someone riding on the train, the light in the moving clock bounces straight up and down between the mirrors, exactly as it does in the stationary clock. The two clocks should tick at the same rate. But from the perspective of someone standing on the platform watching the train go by, the situation looks different. Because the train is moving horizontally while the light bounces vertically, the light in the moving clock does not travel straight up and down. It travels in a zigzag path, like the stitching of a needle through moving fabric. The path of the light is longer, and here is the key. The speed of light is the same for both observers. This is Einstein's second postulate, the one that seems counterintuitive, but that experiment confirms. If the light travels a longer path at the same speed, it takes longer to complete each bounce. The moving clock ticks more slowly. This is not an illusion. This is not a measurement error. This is a genuine physical fact. Time passes more slowly for the moving clock than for the stationary one. A moving clock runs slow. And if all clocks run slow, not just light clocks, but mechanical clocks, biological clocks, the clock of a human heartbeat, then time itself runs slow for moving observers. This phenomenon is called time dilation, and it is one of the most astonishing predictions of special relativity. The mathematics that describes it involves a factor called gamma, which appears throughout the equations of relativity like a recurring theme in a piece of music. Gamma is defined as 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. When the velocity is 0, gamma equals 1 and time passes normally. When the velocity approaches the speed of light, gamma grows without bound and time slows towards stillness. As the velocity approaches the speed of light, the moving clock approaches stopping entirely. The consequences of time dilation are not merely theoretical, they can be measured. Muons, fundamental particles created when cosmic rays strike the upper atmosphere, are produced at altitudes of roughly 10 kilometers above the surface of the Earth. They are unstable, decaying after an average lifetime of about 2 microseconds. In 2 microseconds, even traveling at nearly the speed of light, a muon could cover only about 600 meters. It should never reach the ground, but muons are routinely detected at sea level. The reason is time dilation. Because they are moving at more than 99% of the speed of light relative to us, their internal clocks, their decay processes, run slow from our perspective. They live much longer in our reference frame than their own proper lifetime would suggest, long enough to traverse the full 10 kilometers of atmosphere and reach the ground. The muons are not doing anything extraordinary. They are simply existing, decaying at the rate their physics demands in their own reference frame. It is the difference between their frame and ours that stretches their lifetime. Time dilation is real. It has been measured directly in particle accelerators and in aircraft carrying atomic clocks, and it matches the predictions of special relativity with extraordinary precision. As you rest in the quiet of this night, let that fact settle into you gently. Time is not universal. It is not a fixed background against which events unfold. It is a dimension of the physical world, and like spatial dimensions, it stretches and compresses in response to motion. The universe is stranger than we were taught to believe. And the strangeness follows, inevitably, from two simple principles that Einstein wrote down in a patent office in Bern in 1905. With time dilation established, we have the tools we need to begin the journey toward E equals mc². But before we arrive at the famous equation itself, we need to understand how momentum and energy behave in Einstein's relativistic framework. In classical Newtonian physics, the momentum of an object is simply its mass multiplied by its velocity. A heavy object moving fast has a lot of momentum. A light object moving slowly has little. And the kinetic energy of an object, the energy it has by virtue of its motion, is 1/2 its mass times its velocity squared. These are the familiar equations of everyday mechanics, correct and reliable for objects moving at speeds far below the speed of light. But when we think about very fast-moving objects approaching the speed of light, these familiar equations begin to fail. We need a relativistic version of momentum, one that takes into account the strange relationship between space and time that Einstein's theory demands. The relativistic momentum turns out to be the classical momentum multiplied by gamma, that same factor we encountered in the time dilation equation. The relativistic momentum is the mass times the velocity times gamma. At low velocities, where gamma is very close to 1, this reduces to the familiar classical momentum. But as the velocity approaches the speed of light, gamma grows without bound, and the relativistic momentum grows without bound as well. This has a profound implication. To accelerate an object, you need to apply a force. The force changes the object's momentum over time. But if the momentum grows faster than the velocity, if gamma keeps increasing as you push harder, then pushing harder becomes less and less effective at changing the velocity. The object resists acceleration more and more strongly as it approaches the speed of light. You would need an infinite force, applied for an infinite time, to reach the speed of light. It cannot be done. The speed of light is an absolute upper limit for any massive object. Now, the work done by a force, the energy transferred to an object as it accelerates, is determined by integrating the force over the distance traveled. If we calculate this integral using the relativistic force and carry it through carefully, we arrive at an expression for the kinetic energy of a relativistic object. The calculation requires careful mathematics involving the chain rule of differentiation and a change of variables. But when the algebra settles, the result is beautifully compact. The kinetic energy of a relativistic object is the mass times the speed of light squared times gamma minus 1. This is the relativistic kinetic energy. Let us see what it tells us. At low velocities, where gamma is close to 1, we can use a mathematical approximation, the binomial expansion, to write gamma minus 1 as approximately 1/2 times the velocity squared divided by the speed of light squared. And when we substitute this into our kinetic energy expression, we find that the low-velocity kinetic energy is approximately 1/2 mass times velocity squared. The classical result, the relativistic equation, reduces to the familiar Newtonian formula when the velocity is small compared to the speed of light. Good. This is exactly what we should expect. Any new theory must reproduce the predictions of the old theory in the regime where the old theory has been tested and found to work. But the relativistic expression contains something more than the classical one. Let us rearrange it. The kinetic energy equals gamma times mass times the speed of light squared, minus mass times the speed of light squared. If we think of the total energy as the kinetic energy plus something else, then the total energy is gamma times mass times the speed of light squared. And the something else, the quantity that must be subtracted from the total energy to give the kinetic energy, is simply mass times the speed of light squared. This is the rest energy. This is E equals mc². Let us pause here in the quiet of this night and think carefully about what this means, because this result is not obvious and its implications are among the most profound in the history of physics. The rest energy of an object is the energy it possesses simply by virtue of having mass, regardless of whether it is moving or at rest. It is the energy that is locked in the mass itself. Before Einstein, energy and mass were thought of as entirely separate things. Energy was something that objects possessed in addition to their mass, kinetic energy when they moved, potential energy when they were in certain configurations. But mass itself was not a form of energy. Mass was just mass, an intrinsic property of matter that determined how it responded to forces and how it was pulled by gravity. Einstein's equation changed all of that. It said that mass and energy were not separate things at all. They were different aspects of the same thing, interconvertible, equivalent, related by a constant that was the square of the speed of light. A small amount of mass corresponded to an enormous amount of energy, because the speed of light is so large and its square is larger still. The speed of light is approximately 300 million meters per second. Its square is approximately 90 quadrillion meters squared per second squared. A single kilogram of mass, if it could be entirely converted to energy, would release 90 quadrillion joules, roughly equivalent to the energy released by 20 megatons of nuclear explosive. This is why nuclear weapons are so powerful and nuclear power is so energy-dense. In a nuclear reaction, a tiny fraction of the mass of the reacting materials is converted to energy. In the most powerful nuclear explosions, the mass converted is measured in grams. A few grams of matter, transformed into energy according to Einstein's equation, releases enough energy to destroy a city. In the Sun and in all the stars of the universe, the conversion of mass to energy proceeds every second of every day, on a scale that dwarfs any human technology. In the core of the Sun, hydrogen nuclei are fused together under conditions of extreme temperature and pressure to form helium nuclei. The mass of the helium nucleus produced is slightly less than the combined mass of the hydrogen nuclei that went into making it, about 0.7% less. This missing mass is converted to energy according to E equals mc², and that energy eventually reaches the surface of the Sun and is radiated outward as light and heat. Every second, the Sun converts approximately 4 million tons of mass into energy. It has been doing this for about 4.5 billion years, and it has enough hydrogen remaining to continue for another 5 billion years. The light that warms your skin on a summer day is the energy of converted mass, mass that used to exist in the Sun's core and that now travels as photons at the speed of light across 150 million kilometers of space to reach you. E equals mc² is not merely an abstract truth about the relationship between mass and energy. It is the reason the Sun shines. It is the reason life exists on this planet. It is the equation that underlies the existence of every living thing that has ever drawn breath on Earth. Let your mind rest gently on that thought as the night deepens around you. The equation is not a human invention. It is a discovery, a truth about the universe that was always there, waiting, embedded in the structure of reality, until a 26-year-old patent examiner in Bern followed the logic of two simple principles to their inevitable conclusion. The history of physics is full of moments when a new equation or a new theory revealed something unexpected about the nature of the world. But most such revelations, however surprising, can be absorbed into the existing picture without requiring us to revise our deepest assumptions. E equals mc² is different. It required revising the assumption, held since the beginning of scientific thought, that mass and energy were fundamentally different things. It turned out that this assumption was wrong. Mass is a form of energy. Energy has mass. They are two faces of a single coin. Consider antimatter. Every fundamental particle of matter has a corresponding antiparticle, a particle with the same mass but opposite charge. The antiparticle of the electron is the positron, which has the same mass as the electron but positive charge rather than negative. When a particle and its antiparticle meet, they annihilate each other. Their mass is entirely converted to energy in the form of photons, according to E equals mc². Nothing remains except radiation, pure energy, traveling at the speed of light. the reverse process also occurs. Under the right conditions, when high-energy photons pass near a heavy atomic nucleus, for instance, the energy of the photons can be converted into mass, producing a particle-antiparticle pair from nothing but energy. Matter created from pure light, light created from pure matter. The transformation goes both ways, and the rate of exchange is always E equals mc². This interconvertibility of mass and energy is not a peripheral curiosity of particle physics. It is a fundamental feature of the universe, built into the laws of nature at the deepest level. It is why the universe contains the matter it does. In the very early moments after the Big Bang, when the universe was unimaginably hot and dense, matter and antimatter were created in roughly equal amounts from the intense energy of the primordial state. As the universe expanded and cooled, most of this matter and antimatter annihilated, converting back to energy. But for reasons that physicists still do not fully understand, there was a slight excess of matter over antimatter, about one extra matter particle for every billion particle-antiparticle pairs. This tiny asymmetry is the reason the universe contains matter today. The annihilation of the perfectly matched pairs produced the photons that now constitute the cosmic microwave background, the faint glow of ancient light that fills all of space, a remnant of the earliest moments of existence. The matter that was left over 1 part in a billion became everything. Every galaxy, every star, every planet, every atom in your body. You exist because of a slight imbalance in the matter-antimatter ratio of the early universe. And that ratio, that conversion, that annihilation, that creation was governed at every step by E equals mc². There is one more consequence of Einstein's theory that deserves to be understood before we move toward the full picture of relativistic energy. We have been talking about massive objects, objects that have a non-zero rest mass, that exist at rest in some reference frame, but not all things are like that. Light is not like that. Photons, the fundamental particles of light, have no mass. They cannot be brought to rest in any reference frame. They always travel at exactly the speed of light. If photons have no mass, what does E equals mc² mean for them? If we set the mass to 0, the rest energy is 0. But photons clearly carry energy. We can feel the energy of light as warmth on our skin. We can use it to power solar cells. We can detect individual photons with sensitive instruments. How can massless particles carry energy? The resolution lies in a more general form of the energy-mass-momentum relationship. If we take the equation for the total energy of a massive relativistic object and manipulate it algebraically, squaring both sides, rearranging terms, using the expression for relativistic momentum, we arrive at a more fundamental equation that relates energy, momentum, and mass in a way that works for all particles, massive or massless. The equation is E² equals the momentum squared times the speed of light squared plus the mass squared times the speed of light to the 4th power. This is the energy-momentum relation, and it is one of the most important equations in modern physics. It contains E equals mc² as a special case. Set the momentum to 0, which corresponds to a particle at rest, and you get E² equals mass squared times the speed of light to the 4th, or E equals mass times the speed of light squared. And it tells us what happens for massless particles. Set the mass to 0, and you get E equals the momentum times the speed of light. A massless particle can carry energy and momentum even though it has no mass. This is how photons carry energy. Their energy is not rest energy, they have none. Their energy is entirely kinetic, in a sense, carried by their momentum as they travel at the speed of light. The energy of a photon is proportional to its frequency. High-frequency photons, like gamma rays and X-rays, carry more energy than low-frequency photons, like radio waves. And the momentum of a photon is its energy divided by the speed of light. The energy-momentum relation is the cornerstone of modern particle physics. Every time a particle accelerator produces a collision and detectors measure the energies and momenta of the resulting particles. Physicists use this equation to determine the masses of the particles produced. When the Higgs boson was discovered at the Large Hadron Collider at CERN in 2012, it was discovered not by directly observing the Higgs, but by measuring the energies and momenta of the particles it decayed into and calculating what mass would be consistent with the energy-momentum relation. The Higgs was identified by its mass, by the invariant that every observer in every reference frame agrees upon. And that is perhaps the deepest statement that the energy-momentum relation makes about the structure of the universe. Different observers, moving relative to one another, will measure different energies and different momenta for the same particle. But when they each plug their measurements into the energy-momentum relation and calculate the mass, they all get the same answer. Mass is a relativistic invariant. It does not depend on the frame of reference. In a universe where time dilates and lengths contract and simultaneity is relative, mass is one of the things that everyone agrees on. It is a fixed point in the flowing, relative, observer-dependent landscape of relativistic physics. There is something almost comforting in that. In a theory that has dissolved so many of the certainties of classical physics, that has shown time and space to be flexible and observer-dependent, mass remains invariant. The substance of things endures. As the night wraps more completely around you and sleep grows closer, let us return to the man who discovered all of this, to Einstein himself, and to what his equation meant for his own life and for the world he lived in. The special theory of relativity was published in June of 1905 in a paper titled On the Electrodynamics of Moving Bodies. It was 30 pages long and contained no references to any other published work, not because Einstein was unaware of the literature, but because the paper grew from his own first principles, from the two postulates he had identified as the foundation of the theory, and the argument was self-contained. It was followed, 3 months later, by a short paper of only 3 pages, deriving the mass-energy equivalence as a direct consequence of the relativity paper. The combined effect of these 2 papers, along with 2 other papers Einstein published in the same year, one explaining Brownian motion, confirming the atomic theory of matter, and one explaining the photoelectric effect, for which he would later receive the Nobel Prize, constituted one of the most extraordinary individual contributions to physics in the history of the subject. Einstein called 1905 his miracle year. He was 26 years old. He was a third-class examiner at the Swiss Patent Office. He had no academic position, no laboratory, no graduate students, no institutional support. He had a wife, Malva Marek, a physicist in her own right, who may have contributed to the thinking behind the papers in ways that historians have debated ever since. He had a young son. He had evenings and weekends and the disciplined clarity of a mind that had been working on these problems for nearly a decade. The physics community absorbed the papers slowly. Special relativity was recognized as important almost immediately, though some physicists, including Hendrik Lorentz and Henri Poincaré, who had independently been working on related ideas, had reservations about the physical interpretation Einstein offered. The mass-energy equivalence took somewhat longer to be accepted, not because anyone found a specific flaw in the argument, but because the idea that mass could be converted to energy, that matter and energy were interchangeable, was so far outside the conceptual framework of physics at the time that it required time to be assimilated. Einstein himself was not particularly attached to the fame of the equation. He viewed it as a natural and necessary consequence of the theory, important but not surprising once you understood the reasoning. What surprised him in later life was not the equation but its application. The fact that human beings found a way to harness the mass-energy equivalence for destruction before they found a way to harness it for sustained and peaceful purposes. The atomic bomb, which was developed during the Second World War partly by scientists who fled the very Germany where Einstein had grown up, horrified him. He had signed a letter to President Roosevelt in 1939, the Einstein-Szilard letter, warning of the possibility that Germany might develop an atomic bomb and urging the United States to begin its own research program. He came to regard this letter as one of the great mistakes of his life, even though the warning it contained was entirely correct. Einstein spent the last decades of his life in Princeton, New Jersey, where the Institute for Advanced Study had offered him a position after he left Germany in 1932, never to return. He worked on a unified field theory, an attempt to combine electromagnetism and gravity into a single mathematical framework, without success. He continued to resist the probabilistic interpretation of quantum mechanics, believing that the universe was ultimately deterministic even if quantum mechanics was not. He was sometimes regarded by younger physicists as a brilliant mind that had become detached from the forward march of the field, and yet his stature was undiminished. His presence at the Institute was felt not as a relic, but as a living connection to the deepest questions of physics, still being turned over by the most searching mind of the age. He died in Princeton on April 18, 1955, at the age of 76, of a ruptured aortic aneurysm. He refused surgery, saying that it was tasteless to prolong life artificially and that he had done his share. He was buried without ceremony, his ashes scattered at an undisclosed location. He had requested that his home address not become a place of pilgrimage. The equation he derived in 1905 is now on the wall of every physics classroom in the world. It is printed on mugs and mouse pads and the covers of popular science books. It is perhaps the most widely known sequence of symbols in human history. And yet most people who know the symbols do not know what they mean, where they come from, or why a patent examiner in Bern arrived at them one afternoon in the spring of 1905. Now you know. And the knowing is more beautiful than the symbol alone, because the symbol is just a shorthand for a long and patient argument. An argument that begins with Galileo on a ship and ends with the conversion of mass into light in the core of every star that shines in the universe tonight. Let us trace the full path one more time, slowly, as you drift towards sleep. It begins with the principle of relativity, Galileo's insight that there is no experiment you can perform inside a closed, uniformly moving system that will tell you whether the system is moving or at rest. The laws of physics are the same. The ball you throw, the pendulum you swing, the fire you light, all behave exactly as they would if the ship, or the train, or the spaceship were standing perfectly still. It continues with Maxwell, who showed in the 1860s that light is an electromagnetic wave, and whose equations predicted that this wave travels at a specific speed, approximately 300,000 kilometers per second. A speed that appears in the equations as a fundamental constant of nature, not relative to any particular medium or reference frame, just a number, 3 times 10 to the 8 meters per second, the same everywhere. And then it arrives at the contradiction. If the laws of physics are the same in all inertial frames, and Maxwell's equations are laws of physics, then the speed of light is the same in all inertial frames. But this cannot be reconciled with the Galilean addition of velocities. Something has to give. Einstein's resolution was audacious. The Galilean addition of velocities was wrong. Not approximately wrong, not wrong only at high speeds, wrong in principle, in a way that could not be detected at low speeds because the correction was too small to measure, but that became significant as speeds approached the speed of light. The correct rule for adding velocities was more complicated, and it had the remarkable property that the speed of light could never be exceeded by any combination of velocities. The reason the Galilean rule was wrong was that it assumed something false, that time and space were absolute, that two observers moving relative to each other would agree on the duration of events and the distances between things. They do not. Moving clocks run slow, moving rulers shrink. Simultaneity is relative. Two events that one observer sees as happening at the same time, another observer moving relative to the first will see as happening at different times. These are not violations of common sense. They are consequences of common sense taken seriously, of insisting that the laws of physics, including Maxwell's equations, must be the same for all observers. The strange behavior of space and time in special relativity follows necessarily from this insistence, with mathematical inevitability. And from the strange behavior of space and time follows the behavior of energy and mass. When we work out the correct, relativistic equation for the kinetic energy of a moving object, integrating the relativistic force over the distance traveled, we find that the total energy of the object is its mass times the speed of light squared times the relativistic factor gamma. And when we look at this expression for an object at rest, when we set the velocity to 0 and gamma to 1, we find that the object still has energy. It has an energy equal to its mass times the speed of light squared. E equals mc². Mass is energy, energy is mass. The two are interconvertible. The rate of exchange is the square of the speed of light, an enormous number, which is why even a small amount of mass corresponds to a staggering amount of energy, and why nuclear reactions and antimatter annihilation are so spectacularly energetic compared to ordinary chemical reactions. The energy-momentum relation that generalizes E equals mc² to all particles, including massless ones, has a final and profound message that deserves to be heard before sleep arrives completely. Mass is a relativistic invariant. Different observers, moving at different velocities, will measure different energies and different momenta for the same particle or the same system. But when they each calculate the quantity E² minus momentum² times c² divided by c to the fourth, they all get the same answer, the mass. The mass does not depend on who is doing the measuring or how fast they are moving. It is a fundamental property of the object, fixed and unchanging, the same in every reference frame. This is one of the deep symmetries of the universe. In a world where so much is relative, where time and space and simultaneity all depend on the observer's motion, mass is an anchor. It is what remains when everything observer-dependent has been stripped away. It is, in a precise mathematical sense, the inner reality of a physical system, the thing that persists across all changes of perspective. When physicists at CERN discovered the Higgs boson in 2012, they discovered it by measuring its mass, by using the energy-momentum relation to compute an invariant from data that was observer-dependent. They were following, in the most literal sense, the logic that Einstein worked out in Bern in 1905. The Higgs boson exists because the universe has a particular mechanism for giving mass to fundamental particles, a mechanism involving a field that permeates all of space and interacts with matter particles, slowing them, giving them resistance to acceleration, giving them the property we call mass. The discovery of the Higgs was the experimental confirmation of this mechanism, the last missing piece of the standard model of particle physics. And all of particle physics, all of nuclear physics, all of astrophysics and cosmology insofar as they depend on the conversion of mass to energy, rests on the foundation that Einstein laid in his miracle year. The equation is not just a formula. It is a window into the deep structure of physical reality, a statement about what mass and energy are and how they relate, derived from the simplest and most elegant of starting points. The night is deep around you now, and the stars outside, if you could see them through whatever walls and clouds and city lights separate you from the sky, are performing E equals mc² at this very moment. Sun, 93 million miles away, is fusing hydrogen into helium in its core, converting 4 million tons of mass into energy every second, and the photons produced in that process will spend tens of thousands of years working their way outward through the dense plasma of the solar interior before finally escaping from the surface and beginning the 8-minute journey to Earth. Some of those photons will warm your face tomorrow. Some will be captured by plants and stored as chemical energy in sugars. Some will drive the weather systems that shape your life. All of them carry energy that was once mass that existed in the sun's core until E equals mc² transformed it into light. The atoms in your body were forged in the cores of stars that died before the sun was born. The carbon in your cells, the oxygen in your blood, the calcium in your bones, all of it was assembled in stellar furnaces through nuclear reactions governed by E equals mc². When those stars died, they scattered their material into space in catastrophic explosions, seeding the interstellar medium with heavy elements. The cloud of gas and dust from which our solar system formed was enriched by those ancient stellar deaths. The Earth was assembled from that enriched material. Life arose from the chemistry of those elements. You are, in the most literal physical sense, made of stardust, made of mass that was once energy, energy that was once mass, cycling and transforming in accordance with the relationship Einstein discovered in 1905. There is something deeply moving about that, not in a sentimental way, but in a precise and physical way. The equation E equals mc² connects you by an unbroken chain of physical causation to the first moments of the universe. The mass of your body was created in stellar furnaces that were themselves created from the primordial hydrogen that condensed from the expanding fireball of the Big Bang. The energy that animates you, the chemical energy of the food you eat, the thermal energy of your body warmth, the electrical energy of your neural activity, all of it ultimately traces back to the conversion of mass to energy and energy to mass, in stellar cores and in the primordial plasma of the early universe, governed at every step by a three-symbol equation that a young man derived in a patent office in Bern 120 years ago. The universe is very old. The equation is very simple, and the connection between them, between the compact truth of E equals mc² and the vast, ancient, ongoing story of mass and energy and light, is one of the most beautiful things that human thought has ever uncovered. The world that Einstein was born into was a world in profound intellectual transition. The 19th century had been, in many ways, the century of classical physics, the period in which the framework established by Newton in the 17th century was extended and elaborated and applied with extraordinary success to a vast range of physical phenomena. By the time Einstein arrived at the ETH in Zurich, the major structures of classical physics were firmly in place. Newtonian mechanics described the motion of objects from falling apples to orbiting planets with a precision that seemed essentially perfect. Thermodynamics had given physicists a deep and rigorous understanding of heat and energy and the direction of natural processes. And Maxwell's electromagnetism had unified electricity, magnetism, and optics into a single mathematical framework of breathtaking scope and elegance. There was, at the end of the 19th century, a widespread sense among physicists that the great work of the field was largely complete. The major laws had been found. What remained was to fill in the details, to apply the known laws to more complex situations, to measure more precisely, to calculate more carefully. Some physicists spoke publicly of the possibility that physics was approaching its end. The edifice was built. Interior decoration remained, but there were cracks in the edifice. Small cracks in places that most physicists were not looking, but real nonetheless. One was the problem of black body radiation, the failure of classical physics to correctly predict the spectrum of light emitted by hot objects, which Planck would resolve in 1900 by introducing the concept of energy quantization, inaugurating quantum mechanics. Another was the Michelson-Morley experiment of 1887, which had attempted to measure the Earth's velocity through the luminiferous ether, the hypothetical medium through which light waves were supposed to travel, and had found nothing. No motion through the ether was detectable. The ether appeared not to exist. The Michelson-Morley experiment was a profound challenge to the physics of the day. If there was no ether, what did light propagate through? And if light propagated through empty space, what did the speed of light measured by Maxwell's equations refer to? Which frame of reference? These were the questions that Einstein resolved, not by explaining the Michelson-Morley result directly, but by identifying its root cause, the constancy of the speed of light in all inertial frames, and building a new theory on that foundation. Einstein, characteristically, arrived at special relativity not through careful analysis of the Michelson-Morley data, but through pure thought, through the thought experiments he had been conducting since the age of 16, through the philosophical analysis of what it meant to measure time and distance, through the conviction that the laws of physics must be the same for all observers. He was a theoretical physicist in the deepest sense, someone who worked primarily with ideas and their logical consequences, who trusted the mathematics when it led somewhere unexpected, who was willing to follow an argument all the way to its conclusion, even when the conclusion seemed to contradict common sense. The patience of that approach, the willingness to think slowly, carefully, without rushing to conclusions, is part of what makes the story of special relativity so instructive. Einstein had been thinking about light and motion since 1895. His miracle year was 1905. 10 years of thinking, interspersed with the necessities of education and military service and job hunting and ordinary life. 10 years before the insights coalesced into the papers that changed physics. The equation E=mc² was not a flash of inspiration, but the culmination of a decade of patient, disciplined, systematic thought. Let that patience be a kind of comfort as you rest. Good thinking takes time. The universe is patient. The truth waits. There is a subtlety in the mass-energy relationship that deserves a little more attention, because it touches on something that is often misunderstood. When we say that mass can be converted to energy, we do not mean that mass disappears and energy appears in its place, as if from nothing. We mean that a physical quantity that we were previously accounting for under the label of mass is now being accounted for under the label of energy. Total amount of energy in the universe, including the energy stored in mass, is conserved. Nothing is created or destroyed. The accounting changes. This is important for understanding nuclear reactions correctly. When uranium-235 undergoes fission in a nuclear reactor, when a neutron strikes the nucleus and splits it into smaller nuclei, releasing energy, the total mass of the products is slightly less than the total mass of the reactants. This missing mass has not vanished. It has been converted to kinetic energy of the reaction products, which eventually becomes heat, which drives turbines, which generates electricity. Mass of the fission products plus the energy released, when the energy is expressed in mass units using E=mc² equals the original mass of the uranium plus the neutron. The accounting balances. Total mass energy is conserved. Similarly, in nuclear fusion, the process that powers the sun, when hydrogen nuclei fuse to form helium, the helium nucleus has slightly less mass than the combined mass of the hydrogen nuclei. This mass difference is released as energy. The photons and other particles produced by the fusion reactions carry this energy outward. When they eventually reach the surface of the sun and escape as sunlight, they carry with them the mass energy that was once nuclear binding energy in the sun's core. The total mass energy of the universe is the same before and after. E=mc² does not violate conservation of energy. It is, in fact, the precise statement of what conservation of energy means in a relativistic universe. This realization that mass energy is conserved, not just energy and not just mass separately, was one of the great unifications in physics. Before special relativity, the conservation of mass and the conservation of energy were two separate laws. Mass was conserved in chemical and nuclear reactions. Energy was conserved in mechanical and thermal processes. They were thought of as independent constraints on physical processes. Einstein's equation showed that they were aspects of a single conservation law, the conservation of mass energy. Mass and energy were different forms of the same underlying quantity, and it was the total of both, properly combined, that was conserved. This unification of previously separate conservation laws is a recurring pattern in the history of physics, and it is always a sign that something deep is being revealed. Maxwell had shown that electricity and magnetism were aspects of a single electromagnetic force. Einstein showed that mass and energy were aspects of a single conserved quantity. Later in the 20th century, quantum field theory would show that the electromagnetic force and the weak nuclear force were aspects of a single electroweak force at high energies. The pattern suggests that as our understanding deepens, the number of fundamental things we need to keep track of decreases. The universe is simpler at the deepest level than it appears from the surface. E equals mc² is part of that simplification. Two things that seemed different turned out to be the same thing. The philosophical implications of this extend beyond physics. We tend, as human beings, to organize our experience in terms of distinct categories: matter and energy, space and time, chance and necessity, self and world. The history of science is, in part, a history of discovering that these apparently distinct categories are aspects of something more unified, more fundamental. Space and time, which Newton treated as entirely separate, were shown by Einstein to be aspects of a single four-dimensional spacetime. Mass and energy, which classical physics treated as separate conserved quantities, were shown to be aspects of a single mass energy. The distinctions we draw, the categories we use, reflect the scale at which we observe the world and the limitations of our ordinary experience. At deeper levels, the world is more unified than our categories suggest. This is not mysticism, it is physics. But it is physics that has something to say about the nature of knowledge and the limits of ordinary intuition. The lesson of special relativity, and of E equals mc² in particular, is that reality at its deepest level does not always look the way ordinary experience leads us to expect. The universe is under no obligation to conform to our intuitions. It is what it is, and our job, the job of science, and to some extent the job of every mind that turns toward the world with curiosity, is to discover what it actually is, rather than insisting that it conform to what we expect. Einstein was supremely good at that. His willingness to question the most basic assumptions about the nature of time, about the relationship between mass and energy, about the foundations of classical physics, was not recklessness. It was disciplined and rigorous and grounded in experiment. But it required a kind of intellectual courage that is rarer than technical ability, the courage to take an idea seriously even when it leads somewhere unexpected, to follow the argument all the way to its conclusion, to trust the mathematics when it contradicts the intuition. The reward for that courage was E equals mc², and all that follows from it. In the decades after Einstein published his Miracle Year papers, the implications of special relativity unfolded with a comprehensiveness that justified every bit of the revolution he had inaugurated. The theory was not merely a correction to Newtonian mechanics at high velocities. It was a fundamental restructuring of the conceptual foundations of physics, and its consequences reached into every corner of the discipline. The connection between special relativity and quantum mechanics, the other great revolution of 20th century physics, was made precise by Paul Dirac in 1928, when he wrote down a relativistic wave equation for the electron. Dirac's equation combined Einstein's special relativity with the quantum mechanical wave equation that Schrödinger had developed 2 years earlier, and the result was a theory of extraordinary depth and precision. The equation predicted, as a mathematical necessity, the existence of a particle with the same mass as the electron but opposite charge, the positron, the first antiparticle ever predicted. When the positron was discovered experimentally in 1932, Dirac's equation was confirmed with a precision that cemented special relativity as an essential ingredient of any fundamental theory of matter. The development of quantum field theory in the 1930s, 40s, and 50s extended these ideas into a complete theoretical framework for the behavior of fundamental particles. In quantum field theory, particles are not the fundamental objects of nature, they are excitations of underlying quantum fields that permeate all of space. The photon is an excitation of the electromagnetic field. The electron is an excitation of the electron field. And the Higgs boson, discovered at CERN in 2012, 60 years after it was predicted, is an excitation of the Higgs field, which interacts with matter particles and gives them mass. The Higgs mechanism is, in a deep sense, the explanation of where the m in E equals mc² comes from. We know from Einstein's equation that mass and energy are equivalent. We know from quantum field theory that particles are excitations of quantum fields. The Higgs mechanism tells us why some particles, when they are produced, have the property of being massive, why they resist acceleration, why they cannot be accelerated to the speed of light. The answer is that they interact with the Higgs field. The stronger the interaction, the greater the mass. The photon does not interact with the Higgs field and is therefore massless. The electron interacts weakly with the Higgs field and has a small mass. The top quark interacts strongly with the Higgs field and has a mass roughly 172 times that of the proton. Understanding mass in this way, as an interaction with a field, rather than an intrinsic property of particles, is a deeper level of understanding than E equals mc² alone provides. E equals mc² tells us that mass is equivalent to energy. The Higgs mechanism tells us why particles have the masses they do. Together, they provide a much more complete picture of what mass actually is. And the Large Hadron Collider's discovery of the Higgs boson was the experimental confirmation that this picture is correct, that the universe actually works the way the equations say it does. Einstein's equation opened a door. Dirac walked through it and found antimatter. Quantum field theorists walked through it and built the standard model of particle physics. Experimental physicists walked through it and found the Higgs. The door that a patent examiner opened in 1905 is still being walked through today. The technological applications of special relativity and of E equals mc² in particular have shaped the modern world in ways that are sometimes visible and sometimes hidden. Most visible and the most consequential in terms of human history are the applications to nuclear technology. Nuclear fission, the splitting of heavy atomic nuclei, was first achieved by Otto Hahn, Fritz Strassmann, and Lise Meitner in 1938. Meitner, who had fled Nazi Germany to Sweden, understood immediately what had happened. She and her nephew Otto Robert Frisch worked out the physics of fission in a matter of days during a winter walk in the Swedish countryside. The energy released in a fission event was far larger than could be explained by any chemical or electromagnetic effect. Only E equals mc² could account for it. The tiny mass difference between the reactants and products was being converted to kinetic energy of the fragments. Meitner and Frisch estimated the energy release, compared it with the measured mass differences, and found agreement with Einstein's equation. Within a year, physicists around the world understood that a chain reaction in which each fission event produced neutrons that triggered further fissions could in principle release energy on a scale far beyond anything previously achieved. The Manhattan Project, begun in 1942, was the American effort to build an atomic weapon before Germany did. The bomb dropped on Hiroshima in August of 1945 killed approximately 140,000 people. The bomb dropped on Nagasaki 3 days later killed another 70,000. The mass converted to energy in each explosion was less than a gram, a tiny fraction of the bomb's total mass. The energy released was equivalent to about 15 and 21 kilotons of conventional explosive, respectively. The shadow of this history falls over E equals mc² in a way that no other equation in physics carries. The equation itself is morally neutral. It is a description of how the universe works, not a prescription for what human beings should do with that knowledge. But the applications human beings have found for it in the decades since Hiroshima and Nagasaki have included both the darkest and some of the most hopeful chapters of the technology's history. Nuclear weapons remain the most destructive devices ever built, and their continued existence, is one of the most serious risks humanity faces. Nuclear power, properly managed, offers a source of energy with very low carbon emissions, relevant to addressing climate change. Nuclear medicine uses radioactive isotopes to diagnose and treat cancer and other diseases, saving hundreds of thousands of lives each year. The knowledge is not the application. The equation is not the bomb. But the responsibility that comes with understanding E equals mc², with knowing that mass can be converted to energy on a scale that can destroy cities or power them, is a responsibility that human civilization is still learning to bear. Einstein knew this. He thought about it for the rest of his life. He was a pacifist, a socialist, a deeply humane man who was horrified by what his equation had helped to enable. He could not have predicted, in 1905, the uses to which the physics would be put. But he lived long enough to see them, and he spent the last years of his life working for nuclear disarmament and international cooperation, believing that the same human intelligence that had discovered the equation might find a way to manage the power it described without destroying itself. Let those thoughts settle gently as you drift deeper into rest. The equation is not the whole story. The science is not the whole story. The human choices made in response to knowledge. That is where the story continues, in the hands and minds of every generation that inherits it. There is a particular aspect of Einstein's character that tends to get lost in the popular image of him as the wild-haired sage of Princeton, the icon of genius, the face on the poster. The image captures something real: his unconventional appearance, his disregard for social convention, his willingness to speak plainly about subjects that other public figures treated with diplomatic caution. But it can obscure the more ordinary human qualities that made him who he was. Einstein was, by all accounts, a man of warmth and humor. He played the violin with genuine passion and considerable skill, finding in music a form of thinking that complemented his physics in ways he often tried to articulate. He loved sailing, not for the speed, but for the contemplative quality of drifting on water, and he was notoriously bad at navigating, a deficiency he found funny. He was a devoted father, though his devotion took forms that were sometimes more intellectual than emotional. He was a loyal friend to those he trusted and implacably opposed to pretension and self-importance in all their forms. He was also a man who carried real grief. His first marriage to Milva Maric was deeply troubled, ending in divorce in 1919, the year he became world famous when Eddington's eclipse observations confirmed general relativity. His relationship with his sons was complicated and sometimes painful. His eldest son, Hans Albert, who became a distinguished hydraulic engineer at Berkeley, maintained a difficult relationship with his father throughout his life, never fully reconciling with the man who had, in his view, sacrificed the family for the physics. His second son, Eduard, who showed early promise as a musician, developed schizophrenia in his 20s and spent most of his adult life in a psychiatric institution in Zurich. Einstein rarely saw him after leaving Europe. The grief of that estrangement stayed with him, and yet the physics continued. General relativity, which extended the special theory to include gravity and accelerating frames of reference, was published in 1915, 10 years after the miracle year. It was a work of even greater depth and mathematical sophistication than special relativity, requiring Einstein to master the differential geometry of curved spaces and to develop new physical intuitions about the relationship between matter, energy, and the geometry of spacetime. The theory predicted phenomena that had no classical explanation: the bending of light by gravity, the precession of Mercury's orbit, the gravitational redshift of light. All of these predictions were subsequently confirmed by observation, and general relativity, in turn, contained the seeds of further implications that Einstein himself found troubling. The equations of general relativity admitted solutions that described an expanding universe, a universe that had begun, in the distant past, in an extremely hot and dense state, and had been expanding and cooling ever since. Einstein initially resisted this implication, adding a cosmological constant to his equations to produce a static universe. He later called this his greatest blunder, when Hubble's observations of distant galaxies confirmed that the universe was indeed expanding, as the equations without the cosmological constant had predicted. The expanding universe meant that the universe had a beginning, what we now call the Big Bang. And the Big Bang, in its earliest moments, was a state of pure energy, radiation so intense and so hot that the distinction between matter and energy was not yet meaningful. As the universe expanded and cooled, energy condensed into mass. Quarks bound together into protons and neutrons combined into atomic nuclei. Nuclei captured electrons and became atoms. The matter we are made of was created, in the moments and hours after the Big Bang, by the process described by E=mc², energy becoming mass as the universe cooled enough to permit stable matter to exist. The equation is not just a statement about the energy stored in existing mass. It is a statement about the process by which mass came to exist in the first place. The universe began in energy. Mass emerged from it, and the relationship between the two, the conversion rate, the equivalence, is E=mc². The modern field of cosmology, the scientific study of the universe as a whole, its origin, evolution, and ultimate fate, rests on the twin foundations of Einstein's general relativity and the quantum mechanics that was developed in the 1920s. The two theories are as yet not fully reconciled. The attempt to combine them into a single coherent framework is one of the great open problems of theoretical physics. But within their respective domains, they are extraordinarily successful, and together they provide the most comprehensive and precise account of the universe that human beings have yet achieved. The cosmological story that emerges from this framework begins with the Big Bang, a moment roughly 13.8 billion years ago when the universe was in a state of extremely high temperature and density. In the first fraction of a second, the universe was so hot that the fundamental forces of nature were unified into a single superforce, and the distinction between different types of particles was not yet meaningful. As the universe expanded and cooled, the forces separated, quarks combined into hadrons, and the asymmetry between matter and antimatter that we mentioned earlier produced the slight excess of matter that would eventually become everything. In the first few minutes, the universe cooled enough for protons and neutrons to combine into atomic nuclei, a process called Big Bang nucleosynthesis. About 380,000 years later, the universe cooled enough for electrons to be captured by nuclei, forming neutral atoms. The universe became transparent to light for the first time, and the photons that were released in that moment, the cosmic microwave background radiation, are still traveling through the universe today, detectable in every direction as a faint glow at microwave frequencies. Over the next several 100 million years, the slight variations in the density of the early universe, tiny quantum fluctuations amplified by the expansion, grew under the influence of gravity into the first stars and galaxies. These early stars were massive and short-lived, burning through their hydrogen fuel in millions rather than billions of years. When they died in supernova explosions, they scattered the heavy elements they had forged in their cores, carbon, oxygen, nitrogen, silicon, iron, into the interstellar medium. Later generations of stars, including our own Sun, formed from this enriched material. E=mc² is present at every stage of this story. In the Big Bang, when energy condensed into mass. In the first stars, when mass was converted back to energy by nuclear fusion. In the supernova explosions that scattered heavy elements across the galaxy. In the formation of planets, when gravitational energy was converted to heat and then radiated away. In the metabolism of every living thing that has ever existed on Earth, converting chemical energy from the mass of food into the kinetic and thermal energy of life. The equation is woven into the fabric of cosmic history from beginning to end. It is not a human concept imposed on the universe. It is a feature of the universe that human beings happen to discover, expressed in the language of mathematics that human minds happen to develop. But it was always there. It was there before Einstein, before the Earth, before the Sun, before the first stars. It is as old as the universe. In the final years of his life, Einstein was often asked what he considered to be the most important lesson of his work. His answers varied, but one theme recurred: the importance of imagination. Not the imagination of fantasy, of inventing things that have no basis in reality, but the imagination of thought experiments, the ability to place oneself mentally in a situation that cannot be physically achieved, and to think carefully about what the laws of physics would imply. The thought experiment of riding alongside a beam of light, which he had been conducting since the age of 16. The thought experiment of dropping a stone from a train window and considering how it looked to observers in different reference frames. The thought experiment of being in a falling elevator, which led him toward general relativity. Thought experiments are not calculations. They are not observations. They are acts of disciplined imagination, the careful, rigorous application of known principles to hypothetical situations, following the logic wherever it leads. Einstein was, perhaps more than any other physicist in history, a master of this form of thinking. His greatest insights came not from laboratory measurements, but from the patient exploration of imaginary scenarios. The thought experiment of the light clock, the clock made of two mirrors and a bouncing photon that we described earlier in this story, is a perfect example. No such clock has ever been built, because no clock can be made with mirrors that reflect light with perfect precision over arbitrary distances. But the thought experiment does not require a real clock. It requires only the constancy of the speed of light and the rules of geometry, specifically the Pythagorean theorem, to derive time dilation. The mathematics is high school level. The insight required to set up the thought experiment correctly, to see that a light clock would reveal the relativistic behavior of time, is the work of genius. Einstein once said that imagination is more important than knowledge. He meant, I think, that the ability to envision what might be true, to project existing principles into new situations and see what they implied, was the essential creative act in physics. Knowledge tells you what is known. Imagination tells you what might be discoverable. The equation E equals mc² was not known before Einstein. It was imagined, derived from principles already known, but applied in a new way to a question about the energy of a moving object and extended to its logical conclusion. That logical conclusion, that mass, is a form of energy, that the two are interconvertible, that the conversion rate is the square of the speed of light, was imagined before it was measured. The measurement confirmed the imagination, and the confirmation changed the world. One of the most remarkable features of E equals mc² is how it connects to everyday experience in ways that are invisible but profound. We do not normally think of ordinary objects as containing stored energy, the energy equivalent of their mass. A 1 kilogram bag of sugar contains, in its rest energy, approximately 9 times 10 to the 16th joules of energy, enough to power a large city for several years. The sugar contains that energy not in any accessible chemical form, but locked in its mass itself, according to Einstein's equation. We cannot easily extract it. The conversion of rest mass to energy requires processes, nuclear reactions, particle-antiparticle annihilation, that are not available to ordinary chemistry. But the energy is there, in every gram of every object in the world, waiting in the mass. This is a strange thought to carry with you through daily life. The chair you are resting in contains, in its rest mass, an amount of energy that would be staggering if it could be released. The air around you contains it. Your own body contains it, roughly 7 times 10 to the 18th joules, if the average human mass of about 70 kilograms were entirely converted to energy. This energy is not accessible in any practical sense, But it is there. It is real. It is a consequence of the physical laws that govern this universe. The fact that we cannot easily access rest mass energy is both a limitation and arguably a fortunate feature of the universe. If rest mass were easily converted to energy, if ordinary matter routinely annihilated and released floods of radiation, the universe as we know it would not be habitable. The stability of matter, the fact that electrons and protons and neutrons are stable particles that persist for extraordinarily long times in ordinary conditions, is what allows the complex chemistry of life to exist. E equals mc² tells us that the mass of those particles is equivalent to an enormous amount of energy. The laws of nature tell us that this energy is mostly inaccessible, locked in the particles themselves, released only under extreme conditions. Both facts together, the equivalence and the inaccessibility, are necessary for a universe of stars and planets and living things. The universe is fine-tuned in ways that physicists do not yet fully understand. The constants of nature, the speed of light, Planck's constant, the gravitational constant, the masses of fundamental particles have the values they do, and the laws of nature take the forms they do, in ways that happen to permit the existence of stable matter, long-lived stars, chemistry, and life. Whether this fine-tuning reflects deep principles as yet undiscovered, or the existence of a vast number of universes with different constants, of which we inhabit one that happens to permit our existence, or something else entirely, is a question that remains open. But E equals mc² sits at the center of it. The relationship between mass and energy, with the specific constant c² connecting them, is one of the features of the universe that makes it what it is. There is one final thought that feels right to share before the story closes completely and sleep takes over. It concerns the nature of understanding itself, what it means to understand something, and what understanding E equals mc² actually gives us. The equation is simple to write. E equals mc², 3 symbols and a relation between them. Anyone can write it. Many people have it on t-shirts. But understanding it, genuinely understanding it, in the sense of knowing where it comes from, what it implies, how it connects to the behavior of light and time and mass and energy in the actual physical universe, is something rarer and more demanding. Einstein once wrote that the most beautiful thing we can experience is the mysterious. It is the source, he said, of all true art and science. He who can no longer pause to wonder and stand wrapped in awe is as good as dead. The ability to be astonished, to look at the world with fresh eyes, to notice that familiar things are strange when you look at them carefully enough, to feel the pull of the unexplained, this was, for Einstein, the essential human quality, the one that made science possible and made life worth living. The mystery of E equals mc² is not fully dispelled by understanding it. Understanding where it comes from the constancy of the speed of light, from the principle of relativity, from the relativistic energy calculation, resolves some of the mystery but deepens others. Why is the speed of light constant? Why is there a universal speed limit? Why should the universe be structured in such a way that mass and energy are interconvertible? These questions do not have simple answers, and they point toward deeper questions still, about the nature of space-time, about the origin of the laws of nature, about why the universe exists at all and takes the particular form it does. The equation is a door. Understanding it opens the door and reveals a corridor. At the end of the corridor, there are more doors. Behind each of those doors, there are more corridors. The universe does not run out of depth. Tonight, you have walked a little way down one of those corridors, from a young boy transfixed by a compass in Ulm to a patent examiner in Bern, following the logic of light and motion to its inevitable conclusion. From the relativity of space and time to the equivalence of mass and energy. From the shining of stars to the formation of atoms in the early universe to the atoms of your own body, each one carrying in its rest mass a tiny stored portion of the energy of the cosmos. You are part of it. The equation describes you as surely as it describes the sun. The mass of your body is energy. The energy that animates you is mass. You are, in the precise language of physics, a local concentration of mass energy in a universe that has been converting one form into the other since the very beginning. That is not a poetic metaphor. It is physics, and it is, in its way, a very beautiful thing to be. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from a compass shown to a young boy in Ulm, through the principle of relativity articulated by Galileo on an imaginary ship, through the strange behavior of light that puzzled Maxwell and Einstein both, through the dilation of time that follows inevitably from Einstein's two postulates, through the relativistic momentum and energy of moving objects, and we have arrived at the most famous equation in physics. Not as a mysterious pronouncement from authority, but as a necessary and beautiful truth that follows from the nature of the universe. E equals mc². Energy equals mass times the speed of light squared. Mass is a form of energy. Energy has mass. The sun shines because of it. The stars were born because of it. You exist because of it. And tonight, lying still and breathing slowly, your body performing its quiet chemical reactions, your neurons doing their gentle electrical work, you are yourself a tiny expression of the same principle, a small, warm, conscious knot of mass and energy in an ancient universe that has been converting one into the other since the very beginning. There is no need to hold any of that tightly now. You can let the details soften into impressions, the compass and the train, the mirrors and the light, the gamma factor and the integral, the three letters and the equation they make. Let them dissolve into the background of your awareness, replaced by nothing more demanding than the rhythm of your own breathing and the warmth of the night around you. The universe will keep converting mass to energy and energy to mass while you sleep. The sun will keep shining. The stars will keep burning. The atoms of your body will keep doing whatever atoms do in the quiet hours, faithfully and precisely, obeying the laws that Einstein uncovered, the laws that were always there, woven into the structure of reality long before any human being thought to look for them. The equation is very old, in the sense that matters. It was true before Einstein wrote it. It was true before the Earth existed. It was true at the first moment of the universe, and it will be true at the last. Let that permanence hold you gently as you drift. Let your breathing slow. Let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well, good night. Still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.